I'm very glad to be here and really enjoyed the talk so far this morning, and I think in some way this will be a sort of natural segue from what David and Aaron have talked about. As Joe mentioned, oh, I lost my slides, but here they are. They're back. Okay. Are they good? Will they stick around? We hope so. Okay. As Joe mentioned, I have a background in physics, so I can't resist from opening up with a quote from one of the most famous physicists of the 20th century, Richard Feynman, in talking about the key to science. So this is from a 1960s lecture, public lecture that Feynman gave, which afterwards you should all go to this URL and watch because it's extremely entertaining, much more so when Feynman says it than when I say it. But he says, here's the key to science. We look for a new law by following a process. First, we guess it, then we compute the consequences, and then we check with experience to see if those consequences pan out. If it disagrees with experiment, it's wrong, and that's it. That's science, right? He's Feynman. He's very Brooklyn about the whole thing, straightforward. So he says, make a theory, make a prediction, and check your prediction, right? And so this sounds really, really simple and straightforward, right? We don't need a whole lot of philosophy. You know, people talked, Aaron and David both talked this morning about making predictions. And so it sounds like we have a very simple recipe. Now, of course, this is a caricature. There's a lot more subtlety, but it's something we can strive for, right? And so it seems like there shouldn't be much controversy over this. But if you look at what actually goes on, there's actually a high-level split in how people approach this. And I think it was hinted at a little bit by the talks this morning, but I'm going to make gross caricatures of these things so that I can point out the differences. And I'm going to use terminology from Leo Breiman's paper in 2001. So this was 18 years ago, but it was actually very prescient. He divided the world into two bins, two cultures, which he called the data culture and the algorithmic culture. So the idea is that in each one of these, X are your inputs, Y are your outputs, and the box is the world, okay? And so on the left, you have the data culture where the goal is to extract some information about nature or some knowledge. And you use interpretable and simple models like linear regressions and logistic regressions, things that you believe might actually teach you something about what's inside the box, right? On the right, you have the data culture, which Breiman was arguing for in the paper was not embraced enough, especially by the statistics community at the time. And the idea there is you have the same inputs and outputs, but you don't care about what's in the box. You just want to know, if you give me the X's, can I predict the Y's? Right, and he says, go ahead and throw whatever you want at these models, decision trees, neural nets, which are all the rage these days. Right, this was 18 years ago. And the goal is to predict. We don't really care about knowing what's in the box. We know maybe that the neural net or the decision tree is not the true model of the world, but if it's useful at predicting things, then maybe that's good enough, right? So that was Breiman's argument. I think the names are the only thing that don't really hold up that much because I think we kind of pull together the data and algorithmic world. So I'm going to rename them. I'm going to keep talking about them and use some updated terms. So this is borrowing some terminology from John Kleinberg and co-authors who have a paper from a few years ago, which is about prediction and policy, which is very nice. And I'm going to use examples from them for a couple of slides. They talk about sort of the explain and the predict culture, which they call kind of informally the beta hat and the Y hat cultures. The idea on the left is you have a model and you want to estimate parameters of the model. So beta here is some parameter in the model, whereas on the right, you don't really care about the inside of the model, you just care about the Y hats, the predictions, right? And we've seen examples of both of those today. And because I'm most familiar with the social science and machine learning worlds, I'm going to use those as sort of the versions of these explain and predict cultures that I'm going to talk about. And they do a nice thing to illustrate the difference between when these different approaches are sort of more useful. So it might be that there are times that you really do need to know the causal mechanism. So I have two caricatures here. On the left, for the explain culture, is a question of, should you do rain dances to make it rain so that your crops grow? This is the example from their paper, okay? And the idea here is you have an intervention, which is the rain dance. You have an outcome, which is whether it rains or not, and you have a payoff, which is whether you have crops to eat, right? And you really care about the causal chain because you're hoping that doing a rain dance is going to make it rain, right? And so there you really care about the model of the world. There's a totally different problem, which is, should you bring your umbrella with you on the way to work today? Right? And that's very different because you don't care necessarily about a mechanistic model of the weather, right? You just want to know, if I have a good prediction of the outcome, then I can choose my intervention such that the payoff is good, right? So regardless of how the world works, if you can predict with perfect accuracy if it's going to rain or not, then I know whether to take my umbrella or not. And that thing doesn't affect whether it rains or not, hopefully, unless the world is really much more terribly adversarial than we think. Okay? So these are two cases in which here you really need the explained culture, here you really need the predict culture, right? But most things are not that pure, and probably you want some blend of both, okay? And so now what I'm going to do to really be terrible is I'm going to pick on each culture, because I think they're both doing things wrong. I'm going to pick on them from other people's work, and then I'm going to tell you about some work that we've done where we kind of learn things about both cultures. So first, the explained culture, sort of the traditional social sciences, and again, with both of these, apologies to everyone in each one of these fields because I'm making a caricature to make a point, not because I think everyone in these fields does things exactly this way. So we've heard a bunch about political science this morning. Here is a well-known political science paper from 2003 from Fearon and Layton about civil war. And so in this paper, what they do is something kind of similar to what Aaron did. They want to predict civil war, but they're doing it at the individual civil war level. So they have a bunch of features about different countries and whether they go to civil war or not. Okay, and one of the main conclusions that they have here is the factors that explain which countries have been at risk for civil war are neither ethnic nor religious characteristics, but rather the conditions that favor insurgency, the economic conditions. Okay, so they point to things like population and poverty and things like that, as opposed to some sort of ethnic fractionalization or something like that, right? And so this was a very impactful paper, far beyond just having a lot of citations in the academic world. It was literally headline news, which I'll show you in a second, but let me show you the results. The results look like this, which I think is a nice sort of toy version of what the results look like in social science, a table of regression coefficients. So don't stare at it and try to understand what's there. Every time I look at it, it hurts my head quite a bit. The lights have gone down so you can stare a little more, but you're still not going to see it. I'm going to give you a breakdown of what they do. So here, that column on the left is one model. There's a bunch of variables in the model. There's estimates, the beta hats, of how much those things matter. And then they're very hard to see, but there are stars for things that are statistically significant. Okay? And so what's the punchline? The punchline is the things that I circled in green all have stars next to them. So they're statistically significant, so they're probably not due to random chance. And the things in red are not statistically significant, so we can't really say that anything about ethnic or religious fractionalization really does anything in this model, right? And so that's kind of the flavor of the result. That's where that line in the abstract kind of comes from, right? So this is the style. You have this model. Maybe you believe this is this linear model is or isn't a good model of the world. We can argue about that. But you look at significance and you say, okay, these are the things I'm going to pay attention to. These are things I'm not going to pay attention to. One thing that I think is interesting about this coming from the world I come from is there is no accuracy number anywhere in the table at all, or the paper, I believe. I've looked for it, I haven't found it. Okay, so we're all in here at a predictive analytics colloquium. There's nothing about the predictive power of this in here. But anyway, we have this model, and they get to this conclusion. And like I said before, this is kind of literally headline news in the sense that this is the New York Times from 2006 saying what really causes civil wars, right? So this is the explained culture. And they talk about exactly that line in the abstract. And it wasn't just the New York Times that cared about this. This is a quote from a paper by Ward that I'll talk about in a second, which is in policy circles, the World Bank actually cared about this, and they were looking at economic interventions as a way of staving off civil wars, right? So you really take this to heart and say, okay, this is the thing we're going to focus on. Can we increase the GDP per capita or something like that to try to prevent these civil wars, right? And so this paper by Ward actually went back and said, maybe if we're at this point, we should start to look at how good this model is for actually predicting civil war. So this is the paper by Ward and co-authors. And they argue that too much attention has been paid to finding statistically significant relationships ignoring predictive power. So they go back, they take the model, they take Fearon and Layton's data, they take that model, and they just say, on the data to which the model is fit, how well does it predict? Very simple. Okay, so here's a table. The model, I should note, is a logistic regression model, so it gives a probability, right? And David talked about converting, these probabilistic forecasts into actual outcomes. So you have a decision to make, like, if it's more than 50% likely that there's a civil war, we'll say there's a civil war. Okay? And so that's what the first line says. There's a 0.5 threshold whenever the model predicts above 0.5, meaning 50%. We'll say there's going to be a civil war. The model predicts 0 out of 107 data points in the data set correctly because it says there's never going to be a war. Okay? And it has no false positives because it never predicts yes. That's fine. Maybe you just don't have the thing calibrated, so you lower the threshold. Right? So let's predict there's going to be a civil war whenever there's a 10% chance or higher. Right? And now you get 15 out of 107 conflicts right, but you get 66 false positives. Right? So meaning things where you think there's going to be a civil war and there is not. Okay, so there's always a trade-off about precision and recall and all these sorts of things, but I think you can kind of get the point the authors are making here that, it's hard to say that you've really explained very much if you really can't predict things with any great level of detail, right? So, they go back and they do a whole critical kind of assessment of this paper and another paper, and they do still find support, even in the predictive sense, for that main line in the abstract, which is interesting. So they find that when they take those variables out, the predictive power goes down quite a bit. So they do seem useful in a predictive sense, but the overall power of the model is relatively low, right? So that's kind of the explained culture, right? It would benefit a little bit, I think, from having some of this predictive assessment. And I think on the flip side, it's easy to say, okay, well, we have all these machine learning tools. Let's just stick with the predict culture. Why even bother with this sort of thing? And so now let me go back and pick on the predict culture, again, making a caricature. It's not that I think that every machine learner does what I'm going to point out, but I think it's useful to think critically about. So how many people are familiar with the Netflix prize? Good number, but not everyone. So this is now kind of old in the sense that you can see Netflix no longer looks like this. This was from 2006, a picture of the prize announcement. The idea was that they would give $1 million to the first person who could improve the quality of their recommendations by 10%. What they mean by that is predicting how many stars you're going to rate a movie. Okay, so there's a scale from 1 to 5 stars. They have a model that kind of predicts how many stars you're going to give, right? And if you can get the root mean squared error 10% lower than they currently had, they would give you $1 million. Okay, this was very exciting, especially for all the academics in the world. Everyone went. We all downloaded the data set and started playing with it. And it was really an interesting competition in the sense that they really sort of positioned it perfectly, that it was hard but not impossible. So it took about 3 years, and it was about as exciting as I think machine learning can get in terms of a horse race. So 2009, 2 teams merged, they win, they get the $1 million. There were actually, that merged team, which is Belcour's Pragmatic Chaos, had a improvement of 10.09%. There was another team called the Ensemble with a 10.10% improvement, but Belcour's Pragmatic Chaos submitted 20 minutes earlier after 3 years. Right? So that is literally, I think, as exciting as it can get. It was down to the wire. They paid out the $1 million. They definitely got a good return on investment in that they got a lot more than $1 million worth of work out of it. So kudos to Netflix. However, if you look 3 years after this, let me get there in a sec. If you look at what they produced, this will make the point that they really didn't care what's in the box. So here's a big scary equation. It's a matrix factorization. It's one of the 70 models in the winning solution. They had to publish it. So I think if you think back to Breiman's things, this really is the black box. It's very hard to know what's going on in this model. This is not a model where you read off the beta hat and you know how the world works, right? But if you look at 2012, we'll get there in a sec. The other point I want to make is there are something like hundreds of millions to billions of parameters in these models. So this is performance on the y-axis and number of parameters on the x-axis. So there are actually 100 million ratings in the data set, and there are 10 billion parameters in the model. Okay, so if you're from traditional social sciences, you might even wonder how that gets fit. There's a lot of magic and regularization that makes that happen. But this really is like the extreme of Breiman's black box, right? And then you go, finally, we're at 2012, there's a blog post by the recommendations team, and it says, Beyond the 5 Stars Part 1. There's a 2-part series. And they say this: we evaluated some of the new methods, because everyone had to actually publish and submit all the code and all that. The additional gains in accuracy that we measured did not seem to justify the engineering effort needed to bring them into a production environment. Also, we totally shifted directions. We didn't care about predicting stars anymore. When was the last time you guys put star ratings on Netflix? You can't do it anymore. It's not there. They actually did away with it as an outcome metric. They look at viewing data and how often you view a substantial fraction of things. So I think this is a nice caricature of what happens in the machine learning world, or what can happen in the machine learning world, where you say, look, we really care about a prediction problem, and we go nuts on that prediction problem, but we lose a little focus as to exactly why we're solving that particular problem. Right? And like David said this morning, how you actually translate, okay, you have a recommender system that outputs lower root mean squared error on star prediction. How does that translate into running the business, keeping customers and all that sort of stuff, right? So I think that can often get lost, right? And so I think we need this kind of blend of the explain and predict culture. So if we point out what's sort of nice here, right? The social science world, the explain world, is focused on a causal and a robust model, an interpretable model. These are great things. There is this focus on statistical significance, which doesn't seem that great because it just tells you whether something doesn't matter, right? Which doesn't seem that desirable. You kind of want to know how much it matters, which is where you get to prediction. But if you look at machine learning, it exploits a lot of correlation without real care for causation. So when you go intervene, if you don't have a good causal model, your model might totally break, right? The models are complicated and hard to understand, but they might give you really good predictive performance. And if that's all you care about, then maybe that's useful, right? But it would be nice to get some sort of blend of these things. So I think one main point here is that it's important to view these as complements and not substitutes. But I think, at least in the academic community, it's very much the case that you will find one camp here and one camp here and not a lot of crosstalk between them. So I think that's something we all have to work on fixing. What I'll say is that in terms of prediction advancing social science, there are a lot of, I think, non-obvious ways that are pointed out by Sendhil Malnathan and Jan Spies for why prediction would help even traditional social science. So the first one is like the umbrella thing. Forecasting is useful by itself. Predictive checks helping to sort of quantify how good an explanation is, right? This idea that you could say, I have 2 models, and I think one is a better explanation of the world than the other. What do you mean by that? You mean probably one makes better predictions than the other, right? It's hard to know how else to quantify that. And especially out of sample, which I'll talk about in a second. David and Aaron have both sort of referenced that. I'll kind of hit that over the head in a second. Predictive models can provide benchmarks for causal theory. So this one's pretty interesting. If you do have a mechanistic model, so we could take Aaron's model of terrorism if we think it's mechanistic enough, and we could throw a random forest on the other extreme and see what the gap is between Aaron's model and that model, and kind of get a sense of how much further does the causal model have to go? What's the gap for predictivity? We can also use it for simpler things. So David kind of pointed to things like multi-level regression models, where you might need something like demographics for an individual, and maybe on social media you don't have that data, but you could use a predictive model to kind of impute that missing data. The final one is that there's a lot of really interesting work going on in the intersection of machine learning and economics, where people are actually looking at updating traditional methods for causal inference to incorporate machine learning models. So things like instrumental variables, matching, or estimating heterogeneous treatment effects are all kind of aided by the machinery of machine learning. The flip side is that there's, I think, a lot of stuff, and I'm kind of in this community, so I'm a little cranky about it. There's a lot of places where I think predictive modeling can go wrong. And David kind of pointed out this idea that you want to focus on the right prediction problem, which I think is very important. And I think especially in academic papers, you can be very tempted just by the incentive structure to focus on the problem to which the answer is yes, as opposed to the problem that matters, right? So you find something you can predict, you write a paper about it, as opposed to wondering whether that's really the interesting thing to be working on. I think that's a little bit of the equivalent of kind of the p-hacking problem in the statistical hypothesis testing world. And as David and Aaron have both alluded to, this idea of having a model that has the right balance. It's not too overfit to the past such that it underfits to the future. You want it complicated enough to explain what you saw, but not so complicated that it doesn't generalize to what you're going to see. It's very easy, even with large data sets, to exercise a lot of researcher degrees of freedom. So a lot of decisions that you make can overfit to the data, even when you have millions of observations. And I think this has been thrown around. I'm going to show you a little comic that kind of captures the idea of overfitting, just so that we're all clear about it, because I think it's very important. It's probably redundant for a lot of people in here, but it might make you chuckle even if you've seen it before. So this is from XKCD, online comic, and it's talking about overfitting. And very nicely, they use the example of predicting elections. And what the author did here was made a rule that works perfectly for every election up until that election, and then breaks. Okay, so it works perfectly and then completely fails. So in 1788, no one has been elected president before, but Washington was. In 1792, no incumbent has ever been reelected, but Washington was, right? So this rule keeps breaking. So if you were just looking at the training data, looking at the past, you're doing perfectly, right? But then you come along and fail. And it's fun to look at 2012, right? One of these will break. Democratic incumbents never beat taller challengers, and no nominee whose first name contains a K has lost. Okay, so right, you're chuckling at this. We know this is a hilariously stupid model, right? Even though it would have done perfectly on the past, and it will break in, one of them will break in the future. The weird thing is when people work with data, they make models like this all the time, and they don't catch it, because you don't have that intuition to be able to look inside the model and say, oh, that's what it's saying, right? So this is a big thing just for the social sciences, I think, to appreciate in general as they embrace predictive models, is that we don't want to lose sight of looking out of sample and trying to forecast in the future, as opposed to just looking at the historical data, because we will overfit. Okay, so my caricatures of the two cultures are kind of done. And now I'm going to tell you a little bit of my experience in kind of trying to get those two cultures to meet a little bit. And this is a set of studies, really not one study, it's a set of studies over many years with myself and a bunch of colleagues at Yahoo and at Microsoft Research. And I'll try to summarize several of them. The main question is, how predictable is the spread of information? Okay? And so to get that started, I'll show you a tweet. This is from Neil deGrasse Tyson from a couple of years ago when gravitational waves were detected. So he says, in 1916, Einstein predicts gravitational waves. In 1917, he lays the foundations for lasers. And then you wait 100 years, and people use lasers to detect gravitational waves. It's pretty amazing, right? So I come from this physics background. I can't resist being amazed by these things. That's like the extreme pinnacle of predictive power. He's like, just wait 100 years, and you'll see what I say is there, right? It's kind of the exact opposite of what I think Aaron was talking about, right? We have to wait 100 years to know if anything's right, but here he nails it in 100 years. The question I want to ask you guys, get a little audience participation, is, it's a much more shallow question, but how many retweets will this tweet get? How popular will this thing become? So let's do a show of hands. How many people think it will get at least 10 retweets? 100? 1,000? 10,000? 100,000? Million? All right, we topped out 1 million. I'd say the median answer actually was not terrible. The answer is about 22,000 retweets. One thing to appreciate about this, and we see this all the time now, but we get to observe the answer, which is cool, because if you rewind 50 years ago, or even 15 years ago, you couldn't see the answer, right? If somebody shared information, you couldn't see how far it traveled, and this is only some approximate measure of how far it travels. It's limited to this platform. But it's nice in that we have billions of examples of people sharing information and how much other people are passing it on, right? And so the thing I'm going to talk about now for a little bit is trying to predict that number, okay? And I'm actually gonna go, so Aaron talked about sort of, I think the breakdown was forecasting and prediction. Right? So forecasting was kind of this aggregate thing, and individual prediction is gonna be, how far will this tweet go? I'm gonna do that thing. How far will this tweet go, okay? And what I'm gonna argue is actually kind of the same as what Aaron argued, which is, it's hard. Turns out it's hard. It's harder than you'd like. And I'm gonna ask the question of why. Do we need bigger data and better models? Do we need deeper neural networks? Do we need a lot of more, big data? Or is there something inherently unpredictable about what's going on? And I'm gonna try to argue for that second one, kind of similar to what Aaron said. Okay? So I'll show you a few things. First thing, you might recognize these downward sloping lines from Aaron's talk about heavy-tailed distributions. First thing I'm gonna show you is what cascades look like. So I can't reach up all the way to the top, but if you look at that top event, I'm representing one account posting a message and several of its followers reposting it, something like a dozen or 20 or so of its followers reposting it. So that top node with the red lines coming out of it, somebody posts a story and about 20 people repost it. Is that clear to everybody? Great. So that might be something like, a CNN or something. They put a story up there and about 20 people repost it. What a normal cascade looks like is represented by those 10 dots on the top, which is that you post something and absolutely nobody cares and reposts it. That is the modal thing that happens. That happens most of the time. That's the equivalent of the terrorist group that has the one event and then disappears. And if you look at the distribution of cascades, you find that this is overwhelmingly what happens. Just to hit something like 100 people is 1 in a 10,000 type event. Okay, so this is not really the story the viral marketers want to see. They want to see things really going viral in this way. We don't see that very often. We don't see very wide trees. We don't see very deep trees. This was back in 2011 with Eitan Bakshi and Winter Mason, Duncan Watts. So most things don't go anywhere. This is not just for Twitter, so this is not one of my papers, but a colleague, Shard Goyle, Dan Goldstein, and Duncan again. They looked at this on 7 different platforms. Okay, so this is not just a fact about Twitter. This was true for all kinds of things, news being shared on Yahoo, different games people were playing. This kind of idea that the very small, very shallow trees explain almost all of the events you see. Okay, so this is one person and nobody reposts. The second thing is one person and one of their friends reposts. Way out here in the tail with something like 0.3% of the time, a friend of a friend reposts. Okay, that's how you know you got lucky. A friend of a friend reposts. And we see the same thing in terms of size and depth. Basically, when things do go somewhere, it's much more likely that they're kind of this flat broadcast than this very viral type of structure. We actually dug into that a little more because people really care, I think, and everyone knows of examples of events that are much bigger trees, right? And everyone wants to know what happens out there in the tail. I'll show you some examples. So we went through about 1 billion events, and we found examples of things that actually do go viral in the sense that they hit a lot of people, and I'm showing you 6 different cascades. On the upper left is something very much like a CNN type of situation, okay? One post, and then there are so many followers that repost that I don't have enough pixels on the screen for you to see the individual lines. It looks like a big blob. And then some of those followers of followers repost, and it trickles a little bit, but it's basically gone. Down here is the other extreme. This is probably what you have in mind when you think about something going viral, which is that analogy to the common cold, which is that I infect Joe and he infects 2 people and they infect 2 people and so on and so forth. We do see events like this, but they're exceedingly rare. Most of the events we see that are big look like this, but it's actually very, very hard to predict one from the other. Right? And so if you look at the size, it's very hard to predict the structure. If you look at structure, it's very hard to predict the size. So all of these things lead to this general idea that most things don't spread, and there's a lot of unpredictability, but we're going to try to do it anyway. Okay? And I'll show you our first attempt. Here's a ugly plot that I wish I could take back from 2011 and make prettier, of our predicted and actual values for size of cascades. Okay, it's not my favorite plot I ever made, but I'm stuck with it. This is a log scale for predicted size of the cascade, and a log scale for actual size of the cascade. Each dot is one of these posts. Anyone who's ever made one of these predicted actual plots know that you want things along the diagonal, right? The prediction matches up to the actual. It's kind of a mess. There's not enough pixels. You can't really see that things are somewhat concentrated around there, but there's tons of places where we're off by orders of magnitude. Okay, so I think this makes Aaron's point. It's very hard to predict these events, especially when there's heavy-tailed distribution, right? So if we look at the R squared, right, in the actual raw number of reposts, we get something like a 30% R squared, right? So it's not 0, but it's not 100%. We're not nailing these things. And so this was an interesting point because we published this in the computer science world where there's a lot of machine learners. And then we also have shared this with the social science world. So in the social science world, they say 30%, that's great. Actually, that's pretty good. It's hard to predict what people do. And in the computer science world, they say 30% is terrible. You obviously screwed something up. You should be near that 100% mark, right? And so there was some backlash in the computer science world. This question of how much better can we do? And one thing that stuck out in this study was that we built one of these big random forests. We used lots of features. And then we found that actually we could get rid of everything except for one feature and have the same performance, which is that we can just say, imagine somebody is posting something. If I get to look historically at how they do, right, and I just forecast their batting average. So if your tweets on average get 25 reposts, I'll just forecast 25. That's it. That turns out to do as well as the random forest. So we spent a lot of compute cycles to do something we could do with a one-feature model. Right, this is to David's point that when you can do something with a simple model, you should give that a go. But we had to try the complex model too. So the main question here was how much better can we do, right? Do we need lots more data? Do we need a fancier model? What's going on? Okay, and when we asked this question a few years later, we actually had an intern show up, and we said, Travis, can you go and just make a plot of R squared over time of all these papers that have been written about trying to do this and see how much better we've gotten? And he came back and he said, actually, I can't do it because no paper has done the same thing that you guys did, which was a very sad moment. He came and said, okay, here's a list of stuff, and there's a lot of stuff on this slide, but let me read some of the things people have done. They changed the question, they changed the metric, they changed the data set. Will a given user be retweeted? Will a given tweet be retweeted? Will a cascade reach a minimum size? Which of two tweets will spread further? And will a cascade double in size? These are all related to predicting cascade size, but they are not the problem of saying, before a tweet is posted, can you predict how popular it's going to be, right? If you look at the numbers, F1 metrics, accuracies, AUC, they're getting bigger. They're all bigger than 30%, and they're getting bigger, right? So you might have this idea that actually, yeah, we're getting better at this. But it's on a different task, which is kind of weird, with different data sets, right? There's no standard benchmark here. And so, when you see a different question with a different measure of success evaluated on a different subset of data, it's hard to know if you're actually improving. And sort of to make this point, and this is what I mean by the researcher degrees of freedom and the overfitting that can happen with large data sets, it's hard to know what's going on. So we went back and did it ourselves. We actually took our data set and we fixed our model to just be the one feature model of your batting average. And we said, let's change everything else, right? Because what people usually do is change the rest of the stuff, right? We'll fix the data in the model and we'll just play with the other parameters. And so what we'll do is we'll say, maybe we should treat it as a regression task or maybe a classification task. If we do regression, maybe we'll measure R squared or root mean squared error or mean absolute error. If it's classification, maybe we'll measure accuracy or F1 score, or, tons of metrics to choose from. And then in regression, people tend to filter out a lot of data. Maybe we'll throw out the uninteresting stuff. So we'll filter things that have fewer than 1 or 10 or 100 reposts, right? And then we'll work with the rest. In classification, instead of throwing things out, we'll use that as our threshold. So we'll say an event is interesting if it has more than 10 or 100 retweets. And so what we did there, if you look all the way on the left, this is our original paper, okay? So we wrote kind of the equivalent of 24 papers, right, where you chose one of these different combinations. This was the one we wrote originally, but you could have imagined writing any one of these. And if you look at the ones that treat it as classification and put a relatively high threshold on what qualifies as interesting, it looks like you're doing really well. Like your AUC, your area under receiver operator curve, when you try to predict more than 10 tweets is like 95%. That sounds great. If you walk up to somebody with that and say, I have an AUC of 95%, they'll say, great, I'm gonna take your model. When you walk up to them with an R squared of 30%, they say, go back and try again. Right? But really, it's the same data and the same model, right? So I think this is a way in which it's very easy to sort of be tempted to publish things about this, right, and not things about this, and to not keep grinding away at this to try to make this better because you can do better on a different task, right? So I think this is a big problem, same model, same data, and seemingly different answers. So we decided we would go back 5 years later and just redo this with a lot more data and a better model. Okay, so that's what I'm going to show you now. We're going to focus on ex-ante predictions, meaning you can't use any information that comes from any time after the tweet is posted. So you've got to use stuff that you know a priori. That's because we don't want to cheat and say, well, this thing's going to grow because it's already growing. That doesn't really help us think about what makes for a successful piece of content. Make sense? Good. So we took about 1.5 billion tweets containing URLs from 1 month in 2015. We threw out a bunch of spam. We have an internal classifier. We looked at basically the top English-speaking domains, categorized to news, entertainment, videos, images. Think of things like New York Times, YouTube, Instagram, that sort of thing. We're left with about half the data set. So we have 850 million tweets from 50 million different people. That's about 10 times the size of what we did in the 2011 paper. So we got 10x the data. We're going to do the same thing of trying to predict the cascade size. Here's the features that we have. We have basic content features, so we know the domain of the URL. We know when it was posted. We know things about the people, right? So we know number of followers, how active they are, when their account was created. We have topic features. So we went to a lot of trouble. Actually, Travis went to a lot of trouble of fitting one of these fancy topic models to the data so that you could learn things at more than just the token level. So you could know, for instance, that the concepts of car, automobile, vehicle are all related, right? As opposed to just exactly matching on things like car and automobile and making sort of overly specific inferences. And then we have this sort of secret sauce feature that we learned about in the previous paper, which is past success. Okay, so this is all the different features we could use. You guys ready for the punchline? Okay, here's the punchline. You can ignore the thing on the left. You can look at the thing on the right. These are a bunch of different models. This is the R squared. 0 is terrible. 100% would be great. As we look at the basic content models, the things that look at what's in the tweet, we basically get no predictive performance. Okay, so we're down at about 0. If we cheat and we say, you know what, you just posted a news story that somebody else has posted, and we saw how well it did when that other person posted it, maybe we can use that to forecast it. We get a little bump. We're somewhere around maybe a few percent of the variance explained. If we now use things like the number of followers and audience size that you have, we get something like 20% of the variance explained, so that helps. And we can also use topic features about the individual. What does that person typically post about? That doesn't really do much, but then we throw in this past success feature. That's the feature from the previous paper, the batting average, and we jump up to about 40% of the variance explained. Then we throw in a bunch of other stuff, including interactions between all these things, and we don't see anything get any better. Okay, so in 2011, we explained 30% of the variance. Now we explained 40% of the variance. It took a lot of compute cycles to do this, fitting the topic model, fitting this big random forest. We had 850 million examples. Throw all that away, just use the past success feature, and you get 40% of the variance explained. Okay, so things got a little more predictable overall, maybe because of platform changes, maybe because of features we included, but the punchline's kind of the same, which is that this very simple model kind of does as well as the fanciest model we can build, and it seems to be kind of bottoming out in a sense, or plateauing, right? And so, I think that was sort of a tough moment for us because we thought, well, we should be doing a lot better, and also who's going to publish this thing because nobody likes negative results. But The thing we really wondered was, like, maybe we're really missing something. Maybe there's a magic feature out there that really could nail this problem. And this is, maybe we'll take questions at the panel. I'm curious if people have interesting ideas for what we missed. But this is the point where people usually start to think, oh yeah, I know what you forgot. If you guys would have measured X, you'd have it, right? And we can never rule that out. So what we did is we went to simulations. So we went to simulations and we said, take a toy network and now imagine that you know everything about the network and just run a cascade process on it. And this is a world where, of course, it's not the real world, but you know everything about that world. Whereas in the real world, we might be missing features. We can never rule that out. So imagine I take a network here, I seed this node up here with a piece of content, and then at every time step I say there's some probability that that recently infected node can infect its neighbor, maybe 10% chance. So on each neighbor edge, I flip a 10% coin. The ones that light up are newly infected, so Y started off, Z gets infected. Now Z, we flip coins, Z infects both of its neighbors, so on and so forth. When the cascade stops growing, we stop the process, okay? And what we're going to do is we're going to do that about 8 billion times for different settings of who gets seeded and what the probability of heads of the coin is, okay? And in particular, what we'll do is we'll say, take node Y and just repeat this process 1,000 times and look at the variance and outcomes, right? If it's always the same result, then that means actually it's pretty predictable in terms of if you had full information. If it varies a lot, that means you're really shot. You really can't do anything, because even knowing the quality of the content and knowing who it was seeded to, you have unpredictability. Right? And so here is a picture of these simulations. You can focus on just one of the colored lines. Let's pick the yellow one, which says that the coin has a 40% chance of infecting a neighbor at each time step, which is unreasonably high, but we spanned a full range. 10% to 40%. And what we have here is how different in quality the content is. So this is a world in which all the content is the same in infectiousness. All the probability of heads are all 40%. And there, if we actually knew that everything was all the same and all had the same probability of heads, then actually we could get R-squareds that are up around the 90% range. But if we start to increase the diversity in the content, we pretty quickly fall off a cliff where we get down to upper bounds that are 40%, 30%, something like that. I don't really care about the actual numerical value because this is some simulation. It's not the real world. I'm not claiming that this is why we actually see 30 to 40%. But the idea that we have this drop-off, that the world is almost definitely not homogeneous and has some heterogeneity to it, means that we're probably somewhere in this regime, right? And so we can think of this as kind of like a limit or an upper bound on what we might expect to be able to predict. We can do that in another dimension, which is if we keep the content fixed, but now we imagine we have modeling error. So we might be off by 10% in terms of how likely that coin is to turn up heads. We fall off an even steeper cliff in terms of the upper bound and the predictive power, right? And so this is sort of a way in which we kind of think, okay, it's reasonable to expect that actually we might not be able to get to 100% R-squared because we don't think we live in a world with totally homogeneous content that we know exactly the quality of, right? And so for this bit, right, the idea that most things don't spread, but when they do, it's kind of difficult to predict at the individual level, success, right, I think is the main takeaway about information diffusion, about this individual level prediction. It's not that surprising given a lot of stuff that Aaron has said, and when you really look into this heavy-tailed distribution. The best models we have explain less than half of the variance, and they're based primarily on past success, which is totally reasonable, but we haven't really found that feature that kind of breaks this. The performance bound that we get is probably due to randomness in the diffusion process itself rather than our ability to estimate quality, right? So I think that the idea, for me, what this meant was I'm not going to spend the rest of my career trying to get better at this prediction problem, right? I think there are probably better ways to spend my time because I don't think I can get the measurement error down finely enough, and I don't think the world is homogeneous enough such that this is going to be really super tractable. Maybe I'm wrong, but that's the bet I'm going to make now. The other part of this, going back to the beginning of the talk and kind of the philosophical stuff, is right that I think prediction can help advance understanding. It's not just a tool for forecasting should you bring an umbrella. I think it can actually help you do social science in a new and better way. But I think the problem is that when you focus myopically on prediction, especially when you're not held to the outcomes and you're not a key stakeholder, you can kind of abuse it to no end and do a lot of predictive modeling that isn't ultimately very fruitful for people who really do need to solve problems, right? And so I think this, this to me is like it's a terrible picture to me that people have actually explored this sort of tree of possibilities and not even realized they were doing it, that they were ostensibly working on the same question, but getting to such different versions of it that there was not even a coherent conversation about what was going on. And so this idea that we should try to merge the explanation and prediction culture, that we should make it acceptable for people who care about causal and structural models to also incorporate these predictive methods, and that we should tamp down the predictive modeling by caring about explaining the world, I think is an important thing to hope for. I think, especially for the computer science and machine learning world, there's a bunch of guidelines, and we've written these up in the paper that we did this exercise in. There's a bunch of guidelines about how to do this better, okay? So one is improved standards. So the small-scale social sciences, right, have had this big replication crisis. I think we're seeing kind of the same thing in the predictive sense in the computer science and machine learning world. There are lots of papers, right? There's kind of this joke that you find the baseline that everyone is trying to beat, and you implement that. Because that's probably the thing that holds up, as opposed to the latest, greatest thing that was published in this year's machine learning conference, because it might be very brittle. I think there are good solutions to this, which is clamping down the task. So Matt Salganik at Princeton has done a really nice job with this, where he's taken a Netflix-style approach, but to a social science problem. He said, look, here's a bunch of data. I'm going to tell you guys what the problem is that we care about. We care about predicting adverse outcome in at-risk youth. And I'll give you access to data. You can build a model, and then I will evaluate that model without showing you the data that you're evaluated on. And you can try as many times as you like. It's always going to be a new holdout set. And whoever can do best, right, has built some model that might be useful to us, and we can try to understand what's going on there. Short of that, when you don't have someone who's set up a competition like that, you can check yourself by pre-registering a model, right? By saying, maybe I don't have the equivalent of David's election to keep me honest, but I can pre-register my model and say, actually, I'm going to go ahead and make a prediction about something that hasn't happened yet, and I'm going to go check it, and I'm going to clamp down all of my degrees of freedom, right? This would be a very useful thing for people doing academic-style modeling to do, such that they don't cheat themselves. So focusing on models that are both predictive and interpretable would be nice, but the idea that sometimes we just have a complicated world, like Aaron has pointed out, there are lots of contingencies, right? But maybe we can build those into our models and make more predictive models. And at the same time, there might be limits to what we can do. Maybe we shouldn't toil away at that all day, like the example of the information cascade problem. So I will stop there. The two papers I'll mention, one is with Travis, who did all the hard work on that replication, Amit, Ashton, and Duncan. So that's about the information diffusion specifically. And then this broader paper that we have about prediction and explanation, and this kind of trade-off and set of guidelines and recommendations. Thanks.
Thank you very much.